In this video, we're going to be talking about conditional probabilities. So what does it mean to be conditional probability? Well, in a sense, we're going to have two events that are piggyback off one another. So one thing is true, and then based on the fact that that is true, what is the probability of another thing occurring? Or given that something has occurred, what's the probability of the next thing being true or occurring? So we have this equation that we can use for any case, and we got some new notation here. First of all, this slash right here is just pronounced as given. So we could say the probability of event A given event B. So given that event B has occurred, what's the probability that A will occur? In order to do that, we'll find the intersection of our two events, and we'll put that over or divide by the probability of the given or initial condition. All right, so let's try it out here on our first example. Here we have a data table describing some sort of study about new medicine where people have headaches or don't have headaches based on the fact that they took medicine or did not. And so here are the results of that survey or study. In our first question, we're going to find the probability that a participant who took the medicine did not get a headache. So there's our condition, usually called the initial condition, what happened first. So out of the sample set of people who took the medicine, so given that they took the medicine, how many did not get a headache? Well, let's use our formula first, and then I'll try and explain it without the use of a formula, because sometimes that can kind of get in the way of our thinking. In order to solve this, we'll do our intersection first of those two events. So given the intersection of people who took the medicine and did not get a headache, how many people took the medicine and did not get a headache? Well, here's took medicine. Here's people that did not get a headache. So they come together or intersect right here at 53. So 53 out of 100 total people would be the probability of our intersection there. And then the probability of our initial condition, or that first event. Well, how many people took the medicine? We got 65 people taking the medicine. So 65 out of 100 total people would be the probability of that event. So we could then divide those two things. Because they're both out of 100, well, we could simplify and just use a decimal form here. So 53 out of 100 is 0.53, and 65 out of 100 is 0.65. That could be our decimal form. We could convert it to 0.82. We could also convert it to a percentage by moving the decimal point twice to the right or multiplying by 100. So lots of different ways that we can play around with these number types here. Let's try one more here. Out of the people that did not get a headache, how many of them took the medicine? So again, our initial condition, what happens first is that we have a group of people who did not get a headache, and of those people, how many took the medicine? So let's find our intersection first. How many people did not get a headache and took the medicine? So took the medicine and did not get a headache. Again, we got 53. So 53 out of 100 would be our probability. And then second, what's the probability of our initial condition? How many people did not get a headache? No headache. We got a total of 77 people. So 77 out of 100 would be that probability. One more way that we could do this rather than using our decimal form here is we could divide fractions. So if you remember how to divide fractions, we multiply by the reciprocal of the second fraction. So 53 over 100 times, flip that next fraction, 100 over 77. We can see that the hundreds are going to cancel or go away. Multiplying by 100 and dividing by 100 isn't going to get us anywhere. That'll just cancel. So we're left with 53 over 77. And we could turn that into a percent or a decimal by just dividing the top by the bottom. All right, so there is using our formulas. However, let's just think a little bit more logically or critically here, and we don't need to complicate it with that formula. Of the people who took the medicine, how many did not get a headache? So this is our sample space. How many people took the medicine? Well, we got 65 people who took the medicine. Of those 65, how many did not get a headache? Well, 53 did not get a headache. So 53 out of 65. We could have got there a lot faster by simply just thinking a little bit before we plug in and crazy stuff into an equation. Let's try the second one out, thinking that same way. Again, our initial condition is our sample size or sample set. So of the people who did not get a headache, how many of them took the medicine? So how many people did not get a headache? No headache, 77 of those. Out of those 77, how many took the medicine? 53. So we got 53 out of 77. So sometimes with probability, there are equations that we can use, and we can use them for any example. But a lot of times we don't necessarily need an equation to get our ratio. We can just think a little bit. All right, the next couple examples, we're going to be dealing with playing cards. And so in order to do probability with playing cards, you have to understand some things about the playing cards. First of all, there are 52 cards in a deck. And of those 52 cards, there are 4 different symbols on them. They're called suits, and those symbols look like diamonds, hearts, spades, and clubs. And so because we have 4 equal suits or groups, that can be divided into 52 13 times. So there are 13 cards in each suit, or 13 cards that share the same symbol. There's also 2 different colors. There are black and red cards, and so if we divide 52 into 2 different groups there, we have 26 black and 26 red cards. And then lastly, there are these things called face cards, which have faces on them. The king, the queen, and the jack are those cards, and so there are 3 face cards in each suit. So now we should be able to answer pretty much any sort of probability question using playing cards. For example, find the probability that a black card drawn is a jack. So again, what's our initial condition? We drew a black card. Based on the fact that we drew a black card, how many are possible that they are a jack? Well, let's think about how many black cards we have. We have 26 black cards. Of those, how many are black jacks? Well, there's a jack in each suit, but there's only 2 black suits. So there's only 2 jacks out of 26 black cards. And so we could say 2 out of 26 and reduce that to 1 over 13. And that should make sense because out of 13 cards in each suit, 1 of them is a jack. But we could also use our formula, going back and proving it mathematically. We know the intersection of these 2 events, black and jack, there's 2 out of 52. And how many black cards are there? Well, there's 26 out of 52. So because our denominators are the same, we could simply ignore those and say 2 out of 26. Or we could do the division and multiply by the reciprocal. Or we could change them to decimals and divide that. Lots of different ways to play around with it, but we get the same results. Either 1 out of 13 or about 8% probability. All right, one more example to talk through here. This time, find the probability that a face card is drawn, and given that it's a face card, what's the probability that it's a jack? So again, our face card being drawn is the initial condition. So we'll have to think about how many face cards we have, and of those, how many are jacks? So there are 3 face cards in each suit, and there are 4 suits. So that must mean 12 total face cards. Out of those 12 total face cards, how many are jacks? Well, there are 1 in each suit, so 4 total. So 4 out of 12 could be your starting ratio, which we would reduce to 1 out of 3. And again, hopefully that makes sense, because out of 3 face cards, 1 of them is a jack. So about 33%, or 1 out of 3. All right, so there's just a few examples playing around with conditional probabilities. Again, the condition is your sample size, and out of that, what's the next possibility is an easy way to think about it. Or we can use this complicated formula. Good luck finding conditional probabilities.